All right, let's chat. We have a lesson on plate tectonics, and I'm going to have some questions for you throughout the video. So hang with me, and yes, this is Mr. Wegener on TV. Woo! Okay, let's keep going. So plate tectonics. The first thing that we need to know is, if you remember back to our chapter, it all starts with Alfred Wegener. This Alfred Wegener dude, he's the guy that came up with the idea. He said, hey, I bet all the continents were once together in one large continent called Pangaea. You can see Pangaea there on the screen. And he thought all the continents were together. And all the rest of the people, oh, I'm kind of stuck behind here. There's all sorts of people that said, no way, Wegener, you're crazy, you're a moron. There's no way that all the continents were together. So, of course, haters going to hate. After that, let's see what's happening after that. Then, after that, Wegener, he's like, no. Take a look at the shape. We've got South America, we've got Africa. They seem to fit together. And he said there's the shape of these continents indicate that maybe once they were together. Not only that, but he also says take a look at the fossil record. If you see there's fossils of whatever this animal is, I don't know what it is, but there's fossils of the same animal in South America and Africa. If the continents were really far apart, how did that animal get there? Did it swim across the ocean? Or what about this animal over here, whatever this Lastosaurus is? It was on all these continents. Did it swim across the entire world to go to those continents and die? No way. Those continents had to be together. So he's saying, how did the different fossils appear on different continents? That's so weird. Another thing that I pointed out was climate clues. He's looking at all these things and he says, wait, Africa, South America, India, they all have a similar climate, as if they were all once together in one particular spot. He said they all have the same glacial deposits. That means glaciers. It was the same glacier on all these continents. How could you have the same glacier on all the continents if they weren't together? So after putting all this information together, then people are like, hey, Alfred Wegener, you're not a moron. This actually does make sense because they seem to fit together. Also, there's similar fossils on all the different continents. And thirdly, there's glacial evidence from the same glacier on different continents. The only way that would have happened is if these continents were together. And so a lot of people said, hey, Wegener, you all right? We cool now? We down? Anyway, let's continue. Let's keep going. So, the problem that all this came up with was that, so Wegener, he hypothesized all the continents were together. And people said, okay, Wegener, all right. How did they move? How did the continents get from one place to another? Did they just magically move across the globe? How did that happen? And what does Wegener say? He says, I don't know how it happened. And then he died. So there's Wegener. He's dead. He can't explain how the continents move from place to place. He just knows that they were once together. Then steps in this other dude. What's his name? I forget his name. Doesn't really matter. Anyway, he was a captain of a boat during World War II, and he wanted to start mapping the ocean. He says, hey, I'm going to make a map of the ocean floor with my boat. So he starts making a map of the ocean floor, and lo and behold, smack dab in the center of the ocean, what did he find? He found a mid-ocean ridge. He found mountains in the middle of the ocean. Now, he wasn't ready for this. He's like, what's up with that? How did these mountains get here? Great question. And he says, hey, I bet the plate tectonics, or I bet these tectonic plates, they move apart at the mid-ocean ridge. And people are like, wait, what are you talking about? Why would they move apart at the mid? Oh, remember Wegener? He thought all the continents were together. So this guy thinks that at the mid-ocean ridge, they're moving apart. Oh, okay. Now it's starting to make sense. That's called seafloor spreading. That sounds great. But is there any evidence of seafloor spreading? How can we know that this is actually... Oh... How do we know that seafloor spreading is actually happening? One way that we know is that there's underwater volcanoes all along the mid-ocean ridge. Why would there be underwater volcanoes? Because the Earth is splitting apart. The tectonic plates are moving. There certainly can't be any other kind of information. Oh, there's also pillow-shaped rocks. What makes pillow-shaped rocks? A bunch of sleepy fish? No. The pillow-shaped rocks are made when the lava instantly hits cold water. So at the bottom of the ocean, you got cold water, you got lava that comes out, and it makes pillow-shaped rocks. Scientists find pillow-shaped rocks at the bottom of the ocean, and they say, wait, there's volcanoes here. This is interesting. Also, another thing that they found out is that when they go to the mid-ocean ridge and they take rock samples, the youngest crust, the youngest rocks, were found close to the mid-ocean ridge. The older rocks were found further away from the mid-ocean ridge, which means that the new rock is being formed here at the mid-ocean ridge, and it's starting to move away. And as it moves away year after year after year after year, it gets older and older and older, which means the oldest rock is towards the edge here, and the youngest rock is right towards the center. That seems to make sense. A third piece of evidence for this whole seafloor spreading stuff is that there was these magnetic stripes in the ocean floor. Not that you could see the magnetic stripes, but when you pull the rocks out, there's little bits of iron in the rock, and the little bits of iron in this section are all pointing north. The little bits of iron in this section are all pointing south, and then they're pointing north again, which indicates, since we know that the North Pole and the South Pole, they switch every 26,000 years, that indicates, or that means, that these rocks are slowly being formed. And it kind of helps us get an age of some of these rocks. So at the mid-ocean ridge, new rock is being formed, and it's slowly moving outwards. Which means, in the middle of the ocean, the two continents must have been together and then slowly move apart. Oh, that's the seafloor spreading business. Let's keep going. Speaking of seafloor spreading, here's a little image. Right here is the mid-ocean ridge. It looks like a crack in the middle of the ocean. Here's continent A, here's continent B, and they're moving apart from each other. That's the mid-ocean ridge. They're moving apart. The seafloor spreading going on right here. That means the ocean is getting wider at the mid-ocean ridge. Oh, snap! The ocean is getting wider. For real. Let's keep going. So if new land is being formed in the ocean, does that mean the Earth is getting larger because we keep getting new land? Like here's the mid-ocean ridge. Does that mean the planet Earth is going to get bigger? No, that doesn't mean planet Earth is going to get bigger. No, don't be ridiculous. If it gets bigger in one point, it's got to get smaller at another point, which, let's bring up subduction zones. Take a look at this. Old crust is going away. So remember, at the mid-ocean ridge, we're making new crust, but at this point right here, the old crust is actually going down. So it's going underneath this other crust. Why is this crust going down and this crust not going down? It's because this crust right here, this oceanic crust, it's more dense. And since it's more dense, it goes down. And since this continental crust is less dense, it stays up. So, in one part of the world, new crust is being made. At another part of the world, old crust is getting recycled, or it's getting subducted. It's going down, which is pretty cool. Here's the dense crust, the oceanic crust, and here is the not so dense crust, the continental crust. So the Earth is made up of giant plates that are always moving. That's what you mean to tell me. That's exactly right. Take a look at this map. You guys might remember something like this from science class. The Earth is made up of these huge tectonic plates, and these huge tectonic plates are always moving. Take a look right here in the middle of the ocean. We've got South America, we've got Africa. What's happening to the two tectonic plates here? They're moving apart, away from each other. But take a look over here, all along the Pacific plate. Are they moving away from each other? Nay, nay. They are actually crashing into each other. So one plate is getting subducted there. But also take a look at California right here. They're not moving towards each other. They're not moving away from each other. They're sliding past each other. So, are all the plates really moving? Is that what it means? Yup. All the plates are moving. That's what's going on. Yup, I just like that GIF. That's fun. All right, let's keep going. So there are 3 types of plate boundaries, and you might remember this from class. Let's talk about the 3 types of plate boundaries. The first type of plate boundary is a convergent boundary. I thought this was a good GIF because, look, there's some convergence going on. The bumper car is converging with the police car. They're coming together. That is a convergent boundary. Converging means to come together. So what happens at a convergent boundary? Well, there's a few different things that could happen. Here at this convergent boundary, one plate is getting subducted underneath the other. So here's an oceanic plate. It's more dense. Here is a continental plate. It's less dense. And one plate is getting subducted underneath the other. It's going down. That is subduction. Here's another example of subduction. But look at this. There's no oceanic plates here. We've got a continental plate, and we've got another continental plate. And it shows one is getting subducted. I understand that. But look what it's making. When you have 2 continental plates crash into each other, it doesn't make a trench. It makes mountains. They just start to bunch up. So here we've got continental crust and more continental crust forming mountains. All right, so that's at a convergent boundary. You can make a trench, a deep ocean trench, like we have here. Here's our deep ocean trench. Or we could have mountains. Either one of those things could happen at a convergent boundary. Then we have divergent boundaries. Diverge means to go apart from each other. So at this divergent boundary, we've got this piece of land moving this way, this piece of land moving this way. What does it normally create? It normally creates a mid-ocean ridge because we've got volcanic activity right here. We've got some of this magma squirting up right in between. As the 2 plates pull apart, the magma comes up and makes new rock here. Remember, the old rock is towards the edge, old rock is towards the edge. We got new rock right there. Here's another example of a divergent boundary. This is also the seafloor spreading at the mid-ocean ridge. You can see they're moving apart in opposite directions. It's all hunky-dory. It's all good. And then the last kind of boundary is a transformed fault boundary. Here they're actually sliding side by side. And as they slide side by side, they kind of grind against each other. And when they grind against each other, they're not necessarily making mountains. They're not really making trenches. They're making earthquakes. And it's just like 2 pieces of sandpaper scraping against each other. Sometimes they get stuck and the pressure builds, and then it gets all released again and they slide side by side. So that's a transform fault boundary. Well, that's it. How neat is that? Like, we have gone through pretty much an entire chapter on plate tectonics in just a few minutes, and now we know a little bit more about plate tectonics. I'll leave you right there. Hopefully you've answered all the questions that you need to. Take it easy. Have a great day.